Good afternoon, everybody. How are we all doing? Coming up in here, we now have a workshop presented by Nick Cameron on Rust programming techniques. Please make him feel welcome.
Hey, thanks everybody. Thanks for coming for the tutorial. So I'm Nick Cameron. I'm from Mozilla. I'm quite involved in Rust. I lead the tools team. I'm on the compiler team, the language team, and the core team. And today, this is meant to be kind of like an intermediate level tutorial. Hopefully you'll still be able to get something out of it, even if you're kind of a very advanced programmer in Rust or you've never touched Rust before. I'm not going to kind of introduce the syntax, but hopefully if you can program in something, you'll be able to follow along. An alternate title I played around with this talk was kind of thinking in Rust. And what I want you to get, or what I want to help you do, is to really get into kind of like the mindset of an experienced Rust programmer. So you're not kind of like fighting the Rust compiler anymore. You're kind of like working with it and winning. It's mostly going to be kind of like a chalk and talk kind of tutorial. I didn't realize we'd have this awesome room where you could like actually get some really proper work done. But there are going to be like a few exercises, but don't worry if you don't have like a Rust kind of environment set up. Like you can do them on pen and paper if you like. And maybe even using the compiler is going to be cheating for some of them. I'll stop every now and again to ask questions, but please interrupt if you don't understand something or I can clear something up for anyone. Don't wait until the end because it's quite a long tutorial and I'll have forgotten what I was talking about. Okay, so the tutorial is going to be in kind of two halves. The first half is going to be kind of programming in the small, so like how to write better function bodies, how to write better kind of like code, the micro kind of level. So I'm going to cover a few of the really key fundamental data types that every Rust programmer like uses, every Rust program uses a lot. I'm going to talk about some control flow that's maybe not so familiar from other languages, and then I'm going to tell you how to like avoid doing that and write better control flow by using kind of other constructs and some methods on these types. The second half of the tutorial is going to be kind of like programming in the large, although it's more kind of like the medium. I'm not so much going to touch on kind of architectural issues, so much as kind of like design issues. So how to design the kind of like data types and abstractions in your programming, how to do error handling in your program. Before we jump into all of that, though, I just want to kind of like talk about some principles that have gone into kind of like the design of Rust and its libraries, and that will kind of give a theme to this tutorial. Safe and fast. This is like the kind of the foundation of everything in Rust. We want to be like a systems programming language, and that means it has to be fast, like as fast as C or C++, or even like handwritten assembly in a lot of cases. But it has to be safe. Memory safety is like a big selling point in Rust. In this respect, we're kind of as safe as like a higher level garbage collected language. But also safe in other ways. We want to like avoid giving you so many options for shooting yourself in the foot as you have in some programming languages. But really, this is just like, this would be quite cool in a language if you just have safe and fast, right? But actually, this is just like the starting point. This is like what we consider like table stakes for any kind of like new feature in the language. And what we want to kind of like move towards is we want kind of the language as a whole to be kind of ergonomic. We want it to be pleasurable to write Rust code. We want it to be easy to understand when you're reading Rust code. Or debugging Rust code. And so that's kind of like what we want everything in Rust to be, where we want to end up. And that's kind of like a theme for like a lot of the parts of the tutorial. Is I'm going to start by showing you a kind of a basic, maybe naive way of doing something in Rust. And sure, it'll be safe and it'll be fast, because hopefully everything is. But then I'm going to show you a better way to do it, which will give you kind of more concise code and easier to read code and faster to write code. Okay, so let's start programming in the small. So just to let you know what's coming up, the data types we're going to talk about: option, result, and iterator. And I reckon that in any given Rust program, maybe 50% of the types that you ever use are these three types, basically. So these are really kind of fundamental to Rust. And in terms of control flow, we're going to touch on the match statement, which is a kind of pattern matching construct, and iteration in just kind of in general. And we're not quite going to go in this order. We're going to kind of zigzag between kind of data types and control flow. Okay, so I'm going to start with some C code. So this is fairly idiomatic C code, although it's not actually doing very much. Or C++, sorry. We're going to take a pointer to an object of type foo. And of course, we're good programmers, so we're going to do a null check, because it could be a null pointer. And if it's not, then we're going to call a method on this object. So what could go wrong? There's actually quite a lot. I mean, it's pretty easy to forget the null check. I mean, hopefully we're all excellent programmers. No one here would ever forget doing a null check, but it's a pretty easy mistake to make if you're a beginner. And actually, much more common is you don't need the null check because there is some invariant established somewhere else. But of course, it's code, and code evolves, and that invariant changes, and all of a sudden you need a null check where you didn't need it before, but there's no indication in the code that you need one, and so nobody adds it, and so you're missing the null check. This pointer variable could get mutated. I mean, probably not in the function as it's written at the moment, but if this were a more complex function, and especially if that variable is aliased and or it gets passed to some other function, it's actually pretty easy for a variable to get mutated without it being obvious from the code. And pointer could be it could be non-null, but it might be otherwise invalid. So I mean, it could just be a random bunch of numbers, right? Or it could point to memory that's already been freed, or to memory that's never been initialized, and your null check isn't going to catch that. So here's what the same code looks like in Rust, and you don't have any of those problems, which is nice. So let me kind of explain what's going on here. I should say I'm not really going to explore in this tutorial why you're not getting all of those problems, just kind of some of them. You have to take my word for it on the others. So the really interesting things that are happening here, let's start with the type of the pointer we're passing in. So the ampersand foo is a reference to foo. And references are pointers, but they can never be null. Okay? If you want to represent a pointer that might be null, you have to wrap it in this option type. And an option says either you have something or you have nothing. Okay? So it's just like a null pointer, either we've got something and we're pointing, or we've got 0 and we're pointing at nothing, except that it's explicit in the type in Rust. Okay? So you have to opt in, you know that it's there. And unlike a null pointer, you are forced by the type system to check whether you have something or nothing. If you try to just run this G method on the PTR variable, it would be a type error. Instead, we have to use this match statement. And a match does a pattern match, and there are two patterns that this option can be. It can either be some or it can be none. And in the sum case, you can go ahead and use the value that's there, and you know that it's there. And in the none case, we do nothing and we return exactly like we would in the null check. And because of the scoping in this statement, it's impossible to mutate the PTR variable once you've done the equivalent of the null check. So these two key concepts, option and match, I'm just going to kind of drill into these a little bit. So match is an exhaustive pattern matching. It's a little bit like a switch statement, except that we force it to be, the compiler kind of like checks that it will be exhaustive. So here's a really simple example. We've got an enum type with 3 variants, A, B, and C. And assume that X has type foo. We're then going to match that variable. And we've got the 3 cases. Either it's A, or it's B, or it's C. And in each case, we have a code block. And we'd execute the obvious one at runtime. You can use an underscore here to say, like, we're interested in what happens if it's A, and we want kind of like, we're interested in anything else happening. So you don't have to kind of like repeat yourself all the time. And unlike a switch statement, a match statement can be used as an expression. So, and also it binds variables in the pattern matching. So we've changed the enum a little bit. So now the A variant takes a value with it. So if we have a foo, like X is meant to be a foo here, then we've got 3 options. Either it's an A, or it's a B, or it's a C. And if it's an A, then it's carrying with it a 32-bit integer. And so when we pattern match using the match statement, in the A case, we can bind this new variable n to the value, and we can use that value in the code block, and we can kind of return it as the value of the match statement. And in this case, like, all the branches have to have the same type. So in the default case, we use 0, and then we assign all that into the variable little case foo. So that's a very, very brief introduction to match. There's a lot more that match can do. You can have quite fancy patterns. It does deep pattern matching if you have kind of like nested types that you want to match into. There are kind of if guards that you can have on the match arms and so forth. But that's if you're interested in that, you can look it up. The option type. So we've seen kind of like the option type in action before. The option type is not magic. It's not built into the language. It's just a part of the standard library. And it's a perfectly ordinary enum. It has 2 variants, some and none. But it is generic. So in the sum case, we have whatever we instantiate it to. So before we saw we had like an integer as the type parameter. And we can have any type we want in the sum case. It's very easy to use because it's so common. It's part of the Rust prelude. That means like you don't need to import the name or qualify the name when you use it. You can directly use kind of the option or sum or none, the names of the variants, directly in your Rust program. And also enums are kind of optimized cleverly by the compiler, so even though you have like an option of a pointer, and so this seems like it's a little bit more heavyweight than just having a pointer that might be nullable, the compiler will optimize that to the same thing. Okay, so if you know that a pointer will never be 0, which you do, or sorry, the compiler knows, then it will optimize the option representation in memory so that it's just a pointer, and the none case is represented by the null pointer. So it's, that works out to be just as fast and memory efficient as C when you're at runtime. The result type is very similar to the option type. It's just another generic enum. The difference being that whereas with option you either have like something or you have like nothing, with the result type you either have something or you have an explanation of why you have nothing. Okay, so you have like the value type, which is kind of like the success value, and you have like an error type in case an error happened. So I'll just show that in action. Here we've got a very small, slightly silly function. It takes an integer and it returns a result where the success value is an integer and the error value, the error type is a string. In this case, it's just going to be a message about what went wrong. And we're going to use the pattern matching construct match again on the input. And if it's a positive integer, we're going to return success, and we're going to add 10 to the input. And if it's negative, then we're going to give you an error message. And then here you see how we would use this kind of function. So we call on the second line in the main function. We're going to call that function, and we're going to get back either a success with an integer, or we're going to get back the string. And we're going to use match, and we're going to give a message to the user that's appropriate in each case. So just look, is it clear to everyone what's happening in this code? Do I need to explain bits?
It's clear to me what's going on. I just have a question. Why are the type parameters in the order success result type T, error result type E, and not the other way around? So why TE and not ET?
No reason. I mean, success is kind of the... Sorry, I should repeat the question. The question is, why are the type parameters in the order TE and not ET? That is, success type, failure type, and not failure type, success type. And the order of type parameters in Rust is not really important. It doesn't signify anything. Like, we don't have any kind of currying or anything. So, like, it basically doesn't matter what order the type parameters are in. And given that, like, success is more common than like error, hopefully, and so that's the order it's in. Any other? Yep.
Is there any significance to the exclamation mark?
So the question is there any significance to the exclamation mark? Yes. So an exclamation mark means that this is a macro usage rather than a function call. So print line is a macro, not a function, and whenever you use a macro, you have to use an exclamation mark. The reason for that is that there are things that a macro can do that a function call can't do. For example, a macro can hide a return. So, print line probably isn't going to return out of your function, but like other macros might do. So it's to make it clear when you're reading, like that the invariants around, what you can assume this is going to do are different.
Thanks.
Any other questions before I move on? Excellent. Okay, so the result type is absolutely central to Rust error handling. Essentially, it is Rust error handling story. We're going to go into a little bit of detail right now about how you can use it ergonomically, and then we're going to see a bit later in the talk about kind of like designing error handling, but it's result that's really important, okay? And so you often see a function signature which looks like this, like it returns a result of T and an error type, and the way to read that is that it returns a T in the success case, or it can throw this kind of like error. This is not valid Rust syntax, but maybe we'll evolve to something similar to this soon. And I think it's worth making kind of like, or comparing to kind of like error handling mechanisms in other languages. If you're kind of like a diehard C programmer, then you're probably used to kind of like return codes. And result basically works like that, except that you're forced to check it in the same way that you're forced to check for null pointers. So you can imagine, these are the error codes, like when you get like your error type, but like if you have success, then you get the success value passed back at the same time. You can also see this kind of like analogously to exception types in Java or C++, except that there's, when we kind of throw an error, there's kind of nothing special is happening in the language. There's no stack unwinding or whatever else. It's just a regular return from a function. So I want to introduce a few bits of control flow next that make it easier to use types like result. So it's pretty common to see idioms like this with the match statement where we call some function or we do some work, and if there's success, then we do something with the value that we got back. And otherwise, we're just going to do nothing. Actually, this is probably more common with option than with result. You probably want to handle your error and not just do nothing, although that's a strategy. But this is common nevertheless. And so we have a special construct which does essentially kind of non-exhaustive pattern matching, which is if let. So if let matches just a single pattern. So here, like we've got like a result type, and so we're going to match like the OK pattern. And so if we've got kind of OK, we're going to do something with the value we got, and it binds the variable I in the same way as match does. And if it's not that, then we're just going to carry on. Here's another somewhat common idiom in Rust, which is actually more common with result type. We're going to call a function again, like we had h before. And if it's OK, we're going to do something with the variable I. And if there's an error, we're not going to try and handle it. We're just going to throw it again and assume that our caller can handle it in some way. I'm assuming the return type of the function here is result, otherwise this wouldn't work.
Could you just go back one slide very briefly?
This one or this one?
This one.
OK.
I have no idea what's going on.
OK, so like the if let is kind of a single keyword, and then OKI is a pattern, and then equals just is an equals, and then we've got an expression which will be executed, and then we try and match the result of that expression against the pattern. And if it matches, then we do the block.
Next one.
So it has exactly the same semantics as this. Okay, so here's this other idiom where we either take the success or we throw the error. And actually, it's more common to write this like this in Rust, where we're using the kind of like expression-oriented version of the match statement, and we're either binding into a local variable if we had success, or we're throwing the error to be dealt with elsewhere. And this is such a common idiom in Rust that we have some extremely sweet syntax to deal with it, which is this. So when you see like this postfix question mark operator, that's basically doing exactly that match, right? If it was successful, then we keep we keep that variable, bind it into I, and then we can do something with it. And if there was an error, we throw that for our caller to deal with. Okay, so this question mark.
So could you just go back one slide?
Sure.
Okay, yeah. Yep.
And this becomes this. Yep.
So will that work? Obviously that'll work if H and the caller have the same return type. Will it work if they both have result return types, but where T is equal, where E is equal, but T is not?
Okay, so to repeat the question, what happens if the return types are different? It doesn't matter what, it will do type adjustment, yes, is the short answer. It doesn't matter what the T is, and actually the E's can be different as well, as long as the compiler can find a way to convert one into the other, and it's kind of beyond this talk to talk about how we do that, but it can be done.
So
Sorry.
the question mark really here is unwrapping the OK part, and then
Yeah.
and then the error is basically still wrapped. Still
Yes.
Wrapped?
Yes.
Okay, right. So it's kind of like a partial application.
I think it's probably easier to kind of like look at it like this, in that like if the error case is still kind of like wrapped in the result and will be thrown, because the return type for the function has to be result, not the error type. Whereas if we want to use the value, then there's no point about keeping it inside the result, because we know it must be like okay at this point.
Okay, I just kind of have trouble visualizing how the type is inhabited if it's only got like part of the type. Because see like the allows I to inhabit the result type that like wraps it up in the result
Yes.
type. But if you've unwrapped it there, then
So we're not. So the unwrapping kind of happens at the pattern level. So it's the unwrapping is not part of the whole match statement. The unwrapping is like because we're matching the OK pattern, then we're by matching it, we're kind of doing the unwrapping and we're left with the I. Whereas on the case, so I probably should have used a better. That's a local variable called not the capital E, which is the name of the variant, and so there's no unwrapping happening on that case.
okay, right.
Yeah. There's a question over here somewhere.
This is, if this postfix question mark includes that returning out of the function, it's a bit like a macro, so shouldn't there be an exclamation mark as well?
So the question is, this looks a little bit like a macro. Shouldn't there be like an exclamation mark? So the history of this is it used to be a macro. It used to be called try exclamation mark and was a macro. And we wanted the question mark for reasons I'll discuss kind of on the next slide. And basically, it's not a macro, and so it doesn't need it. And if you're looking for like all the places a function can return, well, you look for the return keyword, you look for an exclamation mark, and you look for a question mark. And if you see these bits of punctuation, then you know it could return, and if not, it can't.
Is there an interrobang in the language?
Oh, what, sorry?
Or a question mark followed by an exclamation mark?
No,
It's called an interrobang.
we do not have that.
Maybe another version.
I remember seeing in some previous videos about Rust, example code often used an unwrap, so they didn't have to check for, I guess, errors or null pointers.
I will talk about unwrap a little bit later. The short story is you should never use it. Okay, so this is the simple kind of syntax for question mark. And you often see it in chains of method calls or field lookups like this, where if you did the matching explicitly, this would be like, 10 lines of code, and it'd be really hard to follow what's actually happening here. But in this case, you can actually see quite clearly what's the kind of control flow, what's happening here. It's just a chain of method calls. But if you want to know what the exceptional control flow looks like, it's explicit here, like exactly where you might be kind of throwing out of this function. And so the question mark's this really nice compromise in that it's extremely lightweight, so you can quite easily see what the kind of common case control flow is doing, but it is explicit. And so if you need to know like every possible path of control, you can see it. All right, so having kind of talked about various kind of like control flow constructs, I want to now show you ways you can avoid using them at all. Okay, so there is a lot of methods on the option and result types. I don't have anywhere near enough time to cover them all here, but you should look at the documentation. I think kind of like mastering these things is a really important step to kind of like writing kind of clean, elegant code in Rust. I'm gonna there's kind of like a symmetry between the option and result types, so I'm only going to cover option, but pretty much everything I cover here exists for result as well, either exactly the same or in some variation. So here's kind of a common thing that you often want to do. Look at the second function, this kind of maybe add 4. So we're going to pass in either an integer or not an integer, like nothing at all. And if we get the integer, then we want to add 4 to it and then return that. And if there's nothing there, we're just going to return nothing. Okay, so this is kind of like a really common way to kind of like unpack, do something, repack. And we can express this really simply in Rust with the map function method. So this is a method on the option type. And so we can, if there's something there, then it applies the function that we pass to it. And if there's nothing there, we just pass none out of it. And actually, it's much more common to see kind of this closure form where the function we're going to apply is written in line as a closure. And even if this syntax is a little bit kind of funky, if you're coming from C, then it should be kind of clear what's going on here. X is what we've got in our option, if we indeed have anything at all, and then we're going to return x plus 4. So is it clear to everyone what's going on? Yep.
And I think it's unwrapping and then rewrapping, right? Like the x,
Yes.
that's the integer, and then return value is another option.
Yes. So
Yeah. So
I'll
you need to explain that.
show this on the next slide.
Oh, okay.
Yep.
Why doesn't the question mark work for the option type?
It does. Sorry, the question is, why doesn't the question mark work for the option type? And it does. And you could use that here, but it would actually be a little bit less succinct than doing it this way, because you would have to do the repacking yourself. So you'd have to put the sum in there, whereas that's done as part of the map here. Yeah.
Feel free to defer this question, but given we have map, why do we have the question mark operator? It seems a little bit on the dangerous side when we've got map already.
So the question is, given that you have like this map function, why have the question mark operator as well? It just leads to like better control flow. Like when you have this really common case of like chains like this with the question mark, it's really easy to read like what's going on here. Like a set of kind of like nested map calls is just not as clear.
Okay, is there some kind of syntactic sugar like how Haskell has their monad syntax for this kind of thing?
No, is the short answer. We don't have high kind of type. So the question was, is there like some kind of syntax for doing this in general, I guess, do syntax in Haskell? And the answer is no, we don't have higher kind of types in Rust. We can't really express like the concept of kind of like do in the more general case. So we have stuff like the question mark operator and functions as a replacement. Okay. I lost my place. Where did we get up to? Okay, yeah, I was going to show you the function signature for map, which I had a question about just now. So looking at the function signature, hopefully it's kind of clear what's going on here, even though it's not the clearest function signature. If we look, we see the first argument is self. We have to be explicit in Rust about taking a self or this argument. So that just basically shows that it's a method with a receiver. We see that we take a function, and if you look at the where clause, you see the type of that function. Don't worry about the details, but like the essential bit is we're mapping t to u, where t is the type parameter for the receiver, and u is the type parameter of the option that we return. So in the example here, t and u are the same. They're both I32, but there's no reason they have to be the same in general. Okay, so I want to look at some other methods, and I'm going to go over these a bit more quickly, and I'm just going to show you the type signatures. So one kind of intuitive way you can think of optional result types is like a Boolean, where if you've got some or OK, it's true, and if you've got nothing or error, then it's false. With that interpretation, then it makes sense to want to and or these things together, and indeed we have these functions. So and takes another option, and we can look at the two, and if both of those are true, like some, then we're going to return the second one that we passed in. And if either of them is none, like false, then we return none. Similarly, or does exactly what you would expect. These are actually kind of like more useful if you think about these like maybe in more kind of practical programming terms. So and is kind of like map, except where what your sorry, I've skipped ahead. before getting to this, I should introduce that the and and the or are kind of eager versions of and or, and that there are also kind of like lazy versions of and or. So and then or else, you can think of the Boolean operations and or, but the short-circuiting kind. So and then takes a function, and if the receiver is none, we never execute that function. But if the receiver is some, then we unwrap the receiver, pass it to this function, and if that function gives you some, then that's the result of the whole and then function. Similarly, like or else takes a function, and if the receiver is something, then it never executes. Whereas if it's nothing, then we execute the function. And then you can think like and then is exactly like mapping, but where the function that we're mapping can actually return a none, right? Rather than always succeeding, where we would wrap it back up in the map case, and then lets you execute a function that might return something or might return nothing, but handles like the none case to start with. Similarly, or else, you can think, or as well, you can think of being like about having a default value. So it's saying, if this is something, then great, I'll just keep using it. If there's nothing there, then I'm going to execute this function or use this value, and that's kind of like the default I'm going to use. So these are both like really common, really useful functions on the option and result types. And there's this pattern that often you have the kind of like eager and lazy versions, where the eager version takes a value and the lazy version takes a function that will be executed if necessary. Okay. This is probably another good point to ask if people have questions on these methods.
The or, does the type parameter there? Is that a typo, or does it have to be?
No, the type parameter is on the option. So or requires the argument that's passed to have the same type parameter as the receiver, whereas that's not the case with and. Okay, cool. So another couple of methods. So I said before, option and result are fairly similar, and it's often extremely common that you'll want to convert between them. And so there are methods to convert from an option to a result and vice versa. So OK or turns an option into a result, and the or bit is because you have to supply like the error case if there was nothing there, and there's like a lazy version OK or else of this. Iter is a way to convert an option into an iterator. So if Boolean is one intuition you can have for an option type, you can also think of an option type as a collection. It's kind of like a list which always has 0 or 1 elements in it. So given this intuition of like a list of 0 or 1 elements, then you might want to iterate over those elements. And so iter gives you an iterator back, and we'll see kind of like more details of the iterator next. Okay, so time for an exercise. Basically, here are two functions. These are written kind of badly. So write them really well is the exercise. There's a link in the top right corner for the documentation. You might find it handy to look up the docs for option in order to do this. We can figure this out, and I'm just going to give you a couple of minutes to do it. And if you have any questions as you go along, just kind of stick up your hand. But I'm going to interrupt because I'm already slightly over time. Sorry, but I want to go through what we've talked about. So I'm just going to go through the first function first. So this, if input is none, return none, and then unwrap the input. Well, we can do this much quicker using a try operator. The question mark operator. So this is exactly what's happened in this version. But if we keep reading a little bit further down, then we see that like we're then doing like an if test, and we're going to return none, and otherwise we're going to wrap it all back up in a sum. So that suggests that we can do even better. We can use the and then function that I talked about before, rather than like the try operator. So this is doing like an implicit check on whether it's sum or none, and then we're returning none if we're less than 0. And actually, if you're using nightly Rust, you can do even better than that, because there's a function that hasn't been stabilized in the standard library yet called filter, which does what and then was doing, like with sum or none, but then applies a predicate to the value if there was something there, and effectively kind of like does and then, returns like sum if the predicate is true and none if it's false. Okay, so the second function is a bit simpler. It just has a match statement and it calls the previous function, which returned an option, and it gives you an OK result, or it gives you an error. And this can quite easily be mapped onto the OK or function that we talked about earlier, because this is just converting from the option type into the result type. So does anyone have any questions about the exercise before we move on? Okay, great. So on to iteration and iterators. So I want to start again with an example in C. We've got a ping all function. This is going to take an array of some type foo. It also needs to take the length of that array. It's going to iterate over that array using a standard C for loop, and then it's going to index into that array and call some ping function on every element of the array. What could go wrong? So that length might just be wrong, right? Who knows who's calling this function, right? There's nothing that says they're going to get this right. The array could actually be mutated inside the loop. We could be adding something onto the end, or taking something away, or changing things, or what have you. The counter variable could be mutated. I mean, that would be an obvious error in a simple loop like this, but in more complicated loops, especially if you're mutating the thing you're iterating over, then it's kind of common to mutate the counter. You could have some logic errors. So a really simple one would be, starting at 1 rather than 0, or using less than or equal to rather than less than. These are probably pretty obvious. Hopefully they'd get caught in code review, but who knows? And certainly once you start having like nested iteration, or you're iterating over multiple arrays, or you're going backwards rather than forwards, or you're stepping over multiple elements at a time, it gets much, much easier to make this kind of logic error. Finally, this array is just a pointer, and so it could be null, and we didn't do a null check. And it could be otherwise invalid in the same way that a pointer could be. So there's a lot that could go wrong. Here's the version in Rust. So hopefully the type looks kind of similar. Unlike C, the type includes the length, and so we don't need to separately pass the length. So that's one thing that can't go wrong. Iterating over it is like a much simpler expression. It's a for loop, but it's not like a C for loop. We're just going to, this is going to bind the variable f to each element in foos in sequence, and then we're going to call this ping function on it. So this is already like much better. Hopefully you all agree. But actually it's kind of uncommon to even see like for loops for this kind of simple case, because there's a whole bunch of functions on iterators, just like there's a whole bunch of functions on option and result that let you write kind of like much more succinct code. So here we explicitly have to ask for an iterator over the array using the iter function. And then there's a for each function which just executes the function for each element. So having got this kind of like taste for what's going on, I want to kind of like, oh yeah, sorry, question. Sorry, the question is, what's the benefit of using for each rather than for? I kind of want to make the general point that when we see like other functions that I'm going to introduce next, then it gives you kind of like a nicer kind of control flow. It's more explicit about exactly what's going on. With for each, there's not a lot of benefit over using for. Like it's a more succinct construction. If you're not doing, if this was going to be like a 10-line closure, I would say use a for loop. If it's just like a real simple thing like this, then it's easier to read the code if you use for each. It's just on one line. Okay, let's look at some methods on the iterator type. So option and result were concrete types. I showed you the definitions that are in the standard library. Iterator is a trait, and we're going to cover traits like at the end of this talk. But what the important thing is that like iterator is kind of like an interface of which there are many, many concrete implementations. You may even write your own. It's common to write your own in Rust code. And that, for various reasons, that means that actually looking at the signatures of these functions is not very useful. So I'm going to do this all by example rather than by showing you the signature. Okay, so a vec in Rust is just a resizable array. Here we're just going to create our vec. We're going to call .iter on it to get an iterator, and then we're going to use some functions. So map, just like map on option, applies this function to every element of the iterator and then gives you a new iterator. Filter applies the predicate, and if it's true, it keeps it, and if it's false, dumps it. So this gives you an iterator that's the same size or shorter. And then for each, we've already seen what for each does. It just executes this function on all of these. So what's the output going to be here? You can have a think or shout it out if you're feeling brave. Yeah. So we're just going to print out 2, 3, and 4. Okay, another couple of functions. This time we're going to use a for loop as well. So it's actually pretty common to kind of like get an iterator, manipulate the iterator in some way, and then use a for loop to iterate over the iterator, if you like. So we're going to use the chain function. So chain takes 2 iterators and chains them together. So you get a new iterator that iterates over all the elements in the first iterator, and then all the elements in the second iterator. Enumerate, well, sometimes, so in the for loop we saw earlier, there's no counter variable. But sometimes you want a counter variable, right? It's useful. So enumerate gives you a way to give that back. So enumerate takes an iterator and then gives you back an iterator, which is an iterator over pairs of the counter variable and the value from the original iterator. And so that's when we see the for loop doing some kind of basic pattern matching on the left-hand side here. So I is the counter value and V is the value from that we're iterating over. And then again, we're going to like print stuff out. So what do we think is going to get printed out this time? Yes. So just pop up what's going to get printed out. Okay, finally, the collect method. Like we've gone from a collection, like a vector, into an iterator, but often you want to go back. You've done your iteration, you want to collect back down into a collection. So in the first example here, we're going to get our iterator, we're going to run map, we've seen map just now, and then we're going to get a new vector, which is kind of all the results that we've got. And then in the second example, we're going to do map again, but then we're going to run enumerate. And so this is going to give us an iterator of counter variables and value pairs. And then we're going to collect into a hash map. So we're going to get a map from the counter variables to the values. And the fact that these are 2 quite different things gives you a hint that collect is quite a smart little function. And exactly how it behaves depends on the type that you're expecting, and that's why we need to put some explicit types on the variable declarations, even though usually in Rust we can just infer these. And the output is going to be like a vector and a hash map with these values. Question?
Are there any lazy iterators?
Aha. So the question is, are there any lazy iterators? And all the iterators are lazy, or most of the iterators are lazy.
So I can have an infinite iterator?
Yes.
Sweet.
And there's kind of like, there's functions for taking like a certain segment of that. Yeah, so when I say like this takes one iterator and gives you another one, that's actually not what happens. It happens lazily when you kind of like call one of the terminating functions like collect or for each. Okay, well, I have a question. So we have this vec, right? And we've seen two ways we can iterate over it. And I think intuitively these are very similar. You can see why these might correspond. But it's kind of odd that these are maybe not as close as you might be expecting, right? Like in the first case, we have to explicitly get an iterator. And in the second case, we don't. But we do have an extra ampersand in there. So what exactly is the for loop expecting? Like a for loop is built into the language. Is it expecting a vector? But we saw an array earlier, and we saw kind of some iterator stuff as well. So what's going on here? All right, so let's start at the beginning. Like this vec macro that's creating a vector for us, the type of that is capital V vec. This is not kind of an iterator, which is why in the first expression you have to call .iter to actually get an iterator. But the vec type does implement into iterator, which is a trait, and we'll see what that gives you in a second. But actually, there are multiple implementations. So there's actually an implementation for just vec, which gives you an iterator over the values in vec. And there's an iterator for a reference to vec, which gives you an iterator over a reference to each value in the vec. And seeing as in our for loop, we don't want to kind of use up that vec. We want to have access to it afterwards. It's pretty common that you want to get the references. And so that ampersand before the vec ensures that we get the implementation of into iterator, which is going to give us an iterator over the references rather than values. And what does into iterator do? Into iterator has like a single function which just turns the receiver. I forgot the self bit. Sorry, that should be into iter of self. So it turns that receiver into an iterator. And then the iterator trait, it has a lot of functions. I've been talking about some of them. There's an awful lot more. But the one that you actually, the really kind of like key function is this next function. And it returns an option. We've seen option already. And what happens is if the iterator has been used up, we return none because there's nothing left to give. Otherwise, we return the next element as a sum. So you might have an inkling of how this is going to fit together, but let's kind of like explore a little bit more. So I talked about if let as a control flow statement before. So it's just pattern matching, and if we match the pattern, we execute the block. There's also while let. So while let does exactly like if let, except it keeps doing it. So while let says, while I can match this pattern, execute the block and keep going. And then when I can no longer match that pattern, then I stop. So this is essentially what the for loop boils down to. We run into iter to get ourselves an iterator, and then we repeatedly call iter.next. And whilst that returns a sum variant, we execute the body of the loop. And if it returns none, then we stop. But that's not the end of the story. As we saw before with if let, then you can rewrite that with match. So similarly, like with while let, we can reduce this to even more primitive constructs. But you need to know that there exists loop, which takes no arguments and just loops forever. It's an infinite loop. And also that Rust has a break statement. And so I'm going to get you all to do this as an exercise, which is, can you write this while let loop that we had before to do iteration using these more basic constructs. So I'm just going to give you a couple of minutes to do that. Okay. So hopefully you had some fun with this. I want to kind of like just show you what the solution looks like quickly. So we still need to kind of run the into-iter function to get ourselves an iterator. Then we've got this infinite loop, and we've got a match that will break out if there's nothing left on the iterator. Otherwise, we're going to like assign into a local variable, and this should hopefully remind you a little bit of where we saw the question mark operator earlier and the idiom that led to that. So just to summarize like where we've come from here, like we're looking at the for loop, and I've shown you kind of how you can think of the for loop, like getting rid of this implicit. So a for loop works over an iterator. It takes any iterator, and then by using kind of while let, I've shown you how explicitly we're kind of getting that iterator and then iterating over it, and then shown how like while let itself is can be thought of in even lower level terms. The second part of this probably not too useful, but it is often useful in your Rust code to be able to use while let for kind of various complex kinds of iterations. So that's a really nice thing to kind of have in your toolbox. All right, so that's the end of the first half of the tutorial. It's been slightly more than half the time, but never mind. And in the next section, we're going to talk about programming in the large-ish. So we're going to talk about error handling. We're going to talk about ownership, primarily like as a design principle. And we're going to talk about traits if we have enough time. So, error handling. So my first and most important point, I think, is that you should think of error handling as an architectural concern in your program. Primarily, that means you have to think about it really early in the design process. So when you're thinking, you know, should this app run on a server, or should it have a GUI, or should it have like a RESTful API, like when you're making that level of architectural decisions, you also want to be thinking about, you know, what is the error handling story going to be for this piece of software? And in this section, we're going to go over the kind of decisions you'd be making as part of that. So we talked about result earlier. I told you result was kind of like the fundamental part of the, or a fundamental part of Rust's error handling story. So we've basically kind of, I've been showing you all this code that uses result, but whenever like we've got the error type, we've basically kind of like, you know, ignored that. So what should you do when you get this, when you get the error case of your result? You have a few options. The first option is that you're able to recover somehow. So often a way to recover is like you can pick an appropriate default value. So you know that if this thing succeeded, you've got a value, and if it didn't succeed, then there's a default value I can use. If you were paying attention earlier, you could write this more succinctly using like an OK or function. Unwrap or function. Some people think that an appropriate way to recover from an error is to give it to the user, and this is wrong. It might at some points in your program be appropriate to alert the user that there has been an error, and maybe the user can give you some input to help recover from that. The mistake is, and presumably what is going on here, is that like your actual error types are internal for the to the program. You should almost never actually show your internal error types to the user. This is almost certainly going to give a bad user experience. If you're going to do this, you need some kind of like dedicated code in your software that handles the internal error type and gives you like a a user interface over that you're going to present to the user. Okay, so option number 2 is to just rethrow. So we've seen this before. We've seen this is what the question mark operator is for. This is like I'm in this particular function and I don't know how to recover from this error, so I'm going to just throw it up the stack and hope that my caller or their caller and so on will be able to handle it. Oh yeah, that's the question mark operator. The third option is that you can panic. So a panic is a controlled crash in Rust. So it crashes the current thread, but it does so kind of like cleanly by unwinding the stack. So destructors will get called, and this isn't a seg fault. It's not exploitable, and you can actually catch this panic, or you can catch it at thread boundaries. This doesn't necessarily have to crash your entire process. And you can explicitly do that using the panic macro, but it's much more common to use the unwrap or expect functions on an optional error where if it's okay, then we unwrap, and if it's not okay, then we panic. So these are your 3 options. So the first 2 options are like actual error handling, and the third option is not error handling, basically. And it's acceptable to do that sometimes. Like if you're writing like a very experimental bit of code, then maybe it's okay. But really, we should be doing one of the first 2. And so the obvious question becomes like, which of those 2 should I do? So an intuition I want to try and get across is about kind of the modularity of error handling. And so I want to like think of your code in terms of kind of error modules. Now these are not like, this is not a Rust concept. This is not like something that's actually explicit in your code. And an error module could be smaller than a Rust module, but more commonly it would be bigger than a Rust module. I think quite common is like your error module fits with a whole crate. And an error module like is, so within that error module, you have context-specific ways that you can recover from the errors that happen. Whereas outside, there's no way that you can recover like in a kind of local kind of way. And so instead you want to present enough information so that you can do kind of like try something else completely instead. So to give you a little example of this, like imagine that you're doing some network I/O, okay? So within your error module, and this might be as small as a single function, right? Like you're going to try to use this connection, and maybe you'll get like a would block error back from your system call, or maybe you've got a connection busy kind of error. Well, you can kind of like recover from that in a very context-sensitive way. You can just sleep and then try again, right? But if this doesn't work, then at some point you've got to kind of tell your caller that like you failed to do this I/O, and for them, like whether you got like couldn't get the connection, or whether you got like a would block kind of error, this is useless, right? But they might want to know, well, there was an I/O error trying to connect to this particular IP address, okay? So that's kind of like the difference between like a kind of internal kind of error and an external error, and where you want to convert from one to the other is kind of like the boundary of your error module. And generally, like within an error module, or a common pattern for error handling is that you always rethrow your error when you're inside the error module, and then you have at the kind of boundary of this module, you have like a single place where you try and do recovery. Okay, and if that recovery fails, then you're going to convert the internal error into a kind of public-facing error. And so that's kind of like the intuition that I kind of push as to knowing when you should kind of like throw versus recover, is kind of getting this intuition of kind of like modular error stuff. Actually, do we have any questions about that?
So, memory errors, those, like you have actually referenced out of bounds, which Rust doesn't pick those up at the compile time that you've got on past the end of an array, right?
Yeah.
And so those, how do they fit into the stack? Does that just give you an implicit return, or?
So the question is, how do you deal with out-of-bounds accesses in arrays? And so bounds checking is done at runtime in Rust, and it depends. Like you can index into an array in different ways, will give you different ways of getting the different ways of handling the out-of-bounds error. So if you just use like the square bracket operators and you're out of bounds, then that's going to panic, which you don't want to happen. So if you think that you might possibly access out of bounds, then you should not be using those indexing operations, and you should use an explicit get, which returns an option, I think, either an option or a result. Pretty sure it's an option. And then you can like explicitly check, or you can use the various functions we talked about in the first half to say if this is a if there was something there, then do something, and if it was none, then recover in some way. So that and then how you do it is up to you.
There's no way of recovering from I walked off the end of the array with normal array operators.
Yes, correct. Okay. So if you remember, the result type has two type parameters. It has the value type that we have under success, and it has the error type. Hopefully what value type, that I don't need to talk about that. It's obviously just what you're doing in your function that's going to dictate the value type. What should you use for your error type? Okay, this is kind of a big question. But first of all, result type, I mentioned earlier, it's not magic. It's not built into the language. It's just part of the standard library. And it's actually totally possible to use your own result type. But don't do that. There's very rarely any reason you'd want to do that unless you are re-implementing some really kind of like fundamental library stuff. I can't imagine a scenario where it makes sense to implement your own result type. On the other hand, aliasing the result type is almost always a good idea. If, like, within a module you are using a single error type, then kind of having an alias for that makes your code much clearer.
Does an alias in this case prevent like implicit casting between different aliases? Or
No, you can think of like an alias like this being resolved. Oh, sorry. The question was, does this prevent kind of implicit coercion between your result type and Rust general result type? And the answer is no, and you probably don't want that. Like you want to just be using the result type. You want to be able to interact with the rest of the ecosystem by doing that. But this is just a convenience, so you don't have to keep typing my every kind of function that you have this in, which gets boring really fast.
Is there an option for not having coercion? So that you can promise that something won't change type?
You can. Oh, sorry. So the question, is there an option for not allowing the coercion? So I should clarify that it's not a coercion. Like the aliasing happens, or the de-aliasing, I guess, happens very early in compilation. So as far as the compiler is concerned, these are the same types. It's not that it's being coerced from one type to another. If you do want something that is like an alias but does not coerce, you can use like a unit struct as like a new type trick. But you should definitely not do that with results. Okay, so one option is you use something really simple as your error type. So you could not use anything at all. If this is really early days code, maybe you just want, it's nice to be able to throw errors, but there's maybe no relevant information that you can get in there. And so you can actually just use the void type, which is just the empty parens, and there's no information at all. You could use error codes, like 1, 2, 3 are error codes. That's not very user-friendly, but it's fine for experimental programming. It's pretty common to see people use strings. Like, again, this is not something I recommend in kind of production code, but it's great when you're experimenting. It's very lightweight, and it lets you debug it. The other option is you do this properly, and you have like a struct or an enum with lots of variants and data that it's carrying around, which gives you lots of information for recovering, lots of information that you can give to the user about what went wrong if necessary. And you have but you have some options. You can use like a single error type for all of your code, or you can use multiple error types. So if you're using a single one, it's quite often common to use an enum. So here we're just using the single enum type as our error type, and every possible kind of error gets a different variant, and any data you want is carried along with that. So here we've got like a server error, user error, connection error, whatever else. Alternatively, you can use multiple different error types. So different functions would return different, throw different kinds of errors. So here we've got like a struct for a server error, and that has like quite different data from all the other kind of errors that we might have. In the end, you're going to have to deal with multiple error types anyway, because the standard library is full of different ones of its own kind, so you're going to have to accommodate that. So even though using a single kind of error type is simpler and often kind of like what you want to do, you still have to handle other types. Often, if you're thinking of like this in terms of error modules, you want like one error type per error module, and that's like another way that this intuition of error module is really helpful. And I'd say if you do have multiple types, and if you want to do kind of error handling properly, you should look at the failure library. This is a library for error handling, and it is on a road to being part of the standard library, and hopefully it's going to be widely used in the ecosystem. So it gives your library an advantage. So it lets you handle kind of lots of different kinds of error types very cleanly. It lets you chain errors together. So often you'll have an error that has like an underlying cause, and it lets you deal with that kind of like chain of causes. And it will allow you to have like back traces when these kind of errors get surfaced. And it lets you interoperate very cleanly with the rest of the Rust ecosystem. Oh, and it's extremely easy to use, okay? Like if you have like if this is your error enum, then you can opt into using failure just with this very small derive fail attribute. Question?
It seems to me that there is no error hierarchy as there is in Python or in C++. Is there a reason that Rust chose not to go that way?
Question was, it seems there's no error hierarchy. Is there a reason? And we generally don't have hierarchies in Rust. Like there's no inheritance between data types, so there's no kind of obvious way to even have such a thing. Yeah, is the short answer. It just doesn't kind of like fit with the Rust philosophy of the way we do things to do that. Okay, so what should I do? Like you're a programmer, like what should I do? Like what kind of approach should I have for error handling? So the first question is, are you writing a library or are you writing an application? If you're writing a library, basically you have to do everything properly. If you want other people to use your library, they're going to expect it to have proper error handling. So you need to use your own error type. Don't try and use like a string or an error code or something like opaque like that. You need to like consider like the error boundaries that I was talking about earlier, and you should probably use the failure library. If you're using an application, if you're producing an application, then you want to think about what kind of application that is. If you're writing a script that you're only going to kind of use once and throw away, then just panic everywhere. but like, bear in mind that scripts that you use once and throw away have a tendency to become scripts that get used twice and then go into production and are an essential part of your, business plan. If you're writing like very experimental prototype software, then you probably want to have some quite lightweight error handling. So, something like using a string as an error message is quite a good idea. And if you're putting something in production, then you need to do like with a library, you need to have like a really kind of like full error handling thing. And I should say that it's kind of hard to refactor from a system that panics everywhere into a system with proper error handling. But it's pretty easy to refactor from a system that just uses like strings, say, into something that does proper error handling. So if you're running prototype or experimental software, that's why I say you should kind of do kind of like the basic kind of error handling approach, because it's really easy to factor that into like proper error handling, whereas if you're just panicking everywhere, that's really difficult. Plus, it lets you do stuff like using the question mark operator and easy interaction with some of the standard library types. Okay, so that's the end of this section, and a good place to ask if people have questions. Sorry.
Can you write traits that rely on things having another trait?
Yes. Sorry, the question was, can you write a trait which relies on things having other traits? The answer is yes, but stick around and we can talk about it rather than going into it right now. Cool. Okay, so I have vastly underestimated how long this talk would take. And I only have 7 more minutes, which is probably not enough time to cover even a half of one of the 2 sections that I have left. So I'm happy to kind of stick around, but I think they need to stop video recording at some point and people might want to leave. So now's probably a good place to stop, and anyone's interested, I can carry on.
Probably what I'll say is, firstly, let's thank Nick for everything that he's done so far.
Thank you.
You are all welcome to hang around here through the afternoon tea break, which starts in about 6.5 minutes. But you'll need to be out of here by the start of the next block in here. So at that point, it's pretty much up to Nick whether he wants to hang around and do whatever he wants to do.
Cool. Thank you. Okay. Thanks. So I have 2 sections remaining. One is on ownership and using that for as a kind of principle of designing your Rust programs. And the second section is on traits as an abstraction mechanism in Rust. I figure even going into the coffee break that we only have time for one of those. So does anybody have a preference? So raise your hands if you'd rather hear about ownership. A few, and raise your hands if you'd rather hear about traits. I think the traits have it. Sorry, ownership folk. I'm happy, so I think we'll be done hopefully early in the coffee break, and I'm happy to kind of stick around and talk about ownership if anyone wants to hear about that. So that was everything you missed. Okay, so traits. Traits are the primary abstraction mechanism in Rust. So if you're coming from kind of like many other languages, these are quite kind of novel abstraction mechanism. So Rust is, in the large at least, is a very object-oriented language, but it's certainly not a class-orientated language. And the way that you use traits is very different from the way that you would use classes. And even if you think of them more like interfaces than classes, which they are, then I think designing with traits is very different. So the basic syntax for using traits is pretty simple. You declare a trait using the trait keyword. In the ellipses where I've elided the code, you'd have a bunch of method signatures. And then when you implement a trait for some concrete type, which is what's going on in the second line, then you have to provide the implementations of all those methods. So I'll do a kind of little comparison between classes and traits. So classes are a way to share both behavior and data. Okay, so when you inherit from a class, you inherit the data that's in the superclass, and you inherit the behavior, the methods that are there as well. Whereas traits are only about sharing behavior. You cannot like share data in a trait. That's part of the concrete data types that Rust provides. Classes are mostly hierarchical. I got a question earlier about kind of like why errors aren't hierarchical in Rust, and we don't really have like the kind of hierarchies that you get all over the place in most OO languages. So just like it's actually possible in classes that you can have multiple inheritance, and therefore you have like a DAG of inheritance rather than a tree, it is possible that you have some kind of inheritance between traits in Rust, but it's the exception rather than the rule. And in general, you compose behavior without inheritance. So it's more of kind of, I don't know, an unstructured blob of behavior sharing rather than a hierarchy. So in a class, whether you are sharing behavior is declared when you define the class. So you write out your class and you write the classes that it inherits from. In Rust, declaring the traits you implement is completely different from declaring the concrete data types. And so that means that you can implement a trait for data types that are in any of your kind of like dependency libraries or even in the standard libraries. So it's quite common for, I write my own trait in my code and then I can implement that for the integer types and for string and so forth. So this means all these things together basically make traits a much more flexible sharing mechanism than classes. Traits are also really important in Rust because they're the way that user-defined types can interact with the language itself. Okay, so we saw earlier this iterator trait, and we saw the for loop, which is part of the language. And by implementing the iterator trait, you allow your own like user types to be iterated over using the for loop. Similarly, there is a deref trait, which allows your user-defined types to act like pointers and to take part in kind of the dereferencing that happens with the dot operator and elsewhere. And then there's the index trait, which allows your user-defined types to act like an array and be able to be indexed into with the square bracket operators. And traits are also essential to the safety guarantees in Rust. A really good example of this is the send and sync traits. And these actually don't have any methods in them at all. These are just marker traits. And by implementing these traits, you are making a guarantee to the Rust compiler that your data type is safe to move between threads or to share between threads, respectively. So this is my kind of lightning summary of traits in Rust. Is there any questions about how these work? Yep.
So implementations can be separate. Is there anything that ties the implementation to where the data type is defined? So there's the thing in Haskell with orphan instances of, it's effectively type class, but is that sort of thing?
So the question is, are you restricted in where you can implement a trait for a concrete data type? So the answer is yes. So Rust is structured into crates, which are kind of like the compilation unit, and similar to it's basically kind of like a library. So either the trait or the concrete type must be defined in a crate with the implementation. So you can impl if you define the trait, or you can impl if you define the concrete data type, or both, of course. But you can't impl if you don't know either. And then there's also a really sorry, I shouldn't say really complex. There's a somewhat complex set of rules around coherence, which dictate like what kind of implementations you can have for certain data types. But yeah, we prevent kind of the orphan problem.
So is there a way to prevent two implementations of the same trait for the same data type?
Question is, do we prevent two implementations of the same trait for the same data type? Yes, that's what the coherence rules are for, but I'm not going to explain them because they're complicated. Yeah. Any other questions? Okay, so you should use more traits. This is probably good advice for nearly every Rust programmer. It's tempting. I mean, you can write Rust code without any traits, and especially if you come for... So you can write methods in what we call an inherent impl, which is an impl which doesn't name a trait at all. So these are just methods that are available on the data type without naming a trait. And if you're used to kind of like the OO way of coding, this you can feel quite a natural way. It means you define all your methods on the concrete data type. So it's just combining the data and the behavior. But you should probably avoid doing that. You should use more traits. So by doing so, like, you enable like much better testing. If you take a trait rather than a concrete type, it's really easy to mock out the concrete type and have like a mock object for testing. It makes your code much more extensible. This is especially important if you're writing a library. If you're always expecting a concrete type, your code is not very flexible. Whereas if you have generic code that will accept any type that implements a trait, that's much more flexible and much more extensible, and that's encouraging like reuse of your code. And it also tends to lead to a cleaner design. Like, you can think of the traits as kind of self-documenting code. It tells you what methods are closely associated with each other. It tells you like what the kind of like effect of having all these methods is, and so on and so forth. So it leads to just generally kind of like, by using more traits, you kind of end up with a cleaner, more elegant design usually. But there's always a limit. As with any abstraction mechanism, it's really easy to kind of go overboard and, you know, have the equivalent of a kind of enterprise Java bean type situation. So, you know, I appreciate the trade-offs around abstraction. And it's pretty easy to kind of factor out traits or to split traits up and so forth. So keep revisiting, refactoring your code to make more traits. So what makes a good trait? It should be small. Some traits, as I said, have no methods at all. It's really common for a trait to only have a single method. For traits with more complex functionality, like 3-4 methods, super common. It's really rare to have like a lot of methods. If you have like, you know, pages full of methods, you probably want to refactor. That's kind of, you're having more of a kind of class design mindset there. And they should be independent, so don't make them too small. If every time you're using one trait, you're also using another one, they're probably too tightly coupled, and you want to either merge them or otherwise refactor. And, you know, I've talked about this from the traits perspective, but from the perspective of the concrete data, what makes better data structures? So I told you before that you can have like methods in the inherent impls, and you should probably limit that for behavior that is specific to the data itself. So if you've got like a getter or setter function, that's probably better off as an inherent method. If you've got, I don't know, something very closely tied to the implementation, the same. If you've got behavior that could be specified generically or that constitutes an interface, then that's something that you should factor out into a trait. So hopefully I have enough. So this is an example that I would have introduced in the ownership section. I probably don't even have the time to introduce it properly here right now. But on the right-hand side, here's a set of methods that I might want on this kind of abstraction. So chunk is an abstraction of some memory being managed. So we've got empty to create a new empty chunk. We've got toString, which gives a string representation of a chunk. We've got a debug string, which does the same thing, but for debugging, for a developer rather than a user. We've got getBuffer to get like the underlying memory as an array of bytes, and the size of that buffer and the potential capacity that we have there. This would be not a great way to design this code. It would be better to make this some traits. So first of all, we're going to use some traits from the standard library. Default is a trait that says I can create a default object, and in this case that would be like an empty chunk. Display and debug are ways to convert an object into a string representation aimed for being a user-facing string and a developer-facing string. And then we're going to create our own trait, buffer, which is the kind of collection of methods that we might want for any kind of buffer provider. And then that would let us, for example, have a mock buffer for testing that's always going to return 0 or something like that. Right, so I've really just skimmed the surface of traits. It's a really big topic in Rust. There is like a huge number of like little features around traits in the language that that let you do various things. It's a really good idea to kind of like read up on this stuff, and it's a great way to kind of like improve your design and make you a better programmer. And I think like the best way to do that is to look at some examples. So a few good examples to look at. Servo is the experimental web browser from Rust. They use a lot of traits to of quite small traits.
Do you mind if I start and then start setting up?
Yeah, sure. And the traits often correspond to something that like a web developer would know about, whereas like the concrete data is kind of the internal structures. Chalk is an implementation of the trait system, but this uses traits for everything, and it's great to see like how that kind of like really almost an overuse of traits actually leads to a really great design. And Tokyo is an async I/O library for Rust, and is great if you really want to like blow your mind about traits. I'm going to be told to stop. Here's a summary. We talked about lots of stuff. This is my contact information. Thank you very much for all the paying attention.